A mystery sits at the root of our species, and it has puzzled researchers for more than a century. Of all the continents on Earth, only Africa ever produced beings like us, and the deeper scientists dig, the stranger this exclusivity becomes, because every new fossil, every genetic clue, every layer of ancient soil keeps whispering the same unnerving hint that our evolution began in Africa and nowhere else, as though the continent itself were hiding a missing piece of the story. The mystery feels almost theatrical in the way it plays out in the evidence. Scattered bones showing sudden leaps in anatomy, climatic swings that turned vast regions into deserts overnight, and a single population that somehow endured long enough to give birth to us, while every other hominin species outside Africa went extinct before they even had the chance to matter. And this story you're about to drift through traces that long, dim corridor of time, how ancient climates pushed our ancestors closer to becoming human, how deep rift valleys shaped bodies and brains, how a narrow genetic bottleneck left fingerprints in every modern person, and how the missing evidence still lingers in hints buried beneath African sediment. It's a slow unraveling, a documentary whispered in the dark, guiding you through 3 million years of evolving footsteps, all tied to one continent that kept producing the radical leaps no other place ever managed. So let us glide gently into the landscapes where this began, where the earth trembled in ways that subtly twisted evolution, and where our earliest ancestors wandered without knowing they were becoming something entirely new. There is something calming about pulling back the curtain on deep time, something soft in examining how ancient environments shaped the first upright walkers more like a sculptor than a destroyer. When you picture the African continent around 3 to 4 million years ago, you'll want to imagine a world shifting beneath the feet of creatures like Australopithecus afarensis, not quite ape, not quite human, but something in between, adapting to the unpredictable blend of forests, grasslands, and volcanic upheaval. And it's this combination that formed the cradle of origins, where the earliest sparks of the human lineage flickered. Mainstream science has long called Africa the cradle of humankind, but that phrase barely captures the strangeness of the evidence. Consider the earliest known contenders for our lineage: Sahelanthropus tachidensis around 7 million years ago in Chad, Aurorantuganensis around 6 million years ago in Kenya, and Ardipithecus ramidus about 4.4 million years ago in Ethiopia. These aren't scattered fossils from a worldwide spread. They're all locked within the African continent, forming a tight cluster of origins no matter how far back you look. And what stands out even more is that while Eurasia had apes, Africa had the first hints of beings walking upright, a behavior that would eventually cascade into everything that defines us. But the deeper you examine the evidence, the more it feels as if Africa wasn't just the location where evolution happened. It was the engine that made it possible. The changes in climate across the continent were extreme but rhythmic, switching from humid jungles to arid savannas in cycles influenced by Earth's orbital shifts. These cycles forced hominins to survive environments that never stayed constant, and that constant instability shaped flexibility itself into an evolutionary advantage. That is one of the most important real facts of our origins. Instability births innovation, and Africa was the most ecologically unstable region on Earth during key phases of our evolution. Important fossil sites like Hadar in Ethiopia, Litoli in Tanzania, and Sterkfontein in South Africa reveal a patchwork of ancient ecologies, each pushing early hominins in different ways. In one moment, the land offered lush vegetation. In another, it shifted toward open grasslands where standing upright provided better vantage and longer distance endurance. The famous Litoli footprints, dated to about 3.66 million years ago, show that early hominins walked with a near-human gait long before the emergence of the genus Homo. That alone suggests a quiet revelation. Evolution toward human-like traits began much earlier and much more deeply rooted in African landscapes than once assumed. Now, picture the Rift Valley, a massive geological scar running from Ethiopia down to Mozambique. This cleft wasn't just scenery. It acted like a slow-burning evolutionary furnace. Volcanoes blanketed valleys with ash that preserved fossils with eerie clarity. Shifting tectonic plates created lakes, split habitats, and isolated populations long enough for divergence to occur. This is where many of the transitional species are found, and it's why Africa's fossil record is so uniquely rich for early hominins. Yet, even with this abundance, there are still missing links, species that must have existed but have not yet been unearthed, which is why this opening section also acknowledges the puzzle of absence. African sediments hold countless secrets still buried, and each missing bone hints at a chapter we haven't yet read. One mainstream fact everyone agrees on: the earliest stone tools, Oldowan tools, appear in Africa around 2.6 million years ago. But what matters more is that they appear before any evidence of early humans leaving the continent. That means the dawn of technology happened in Africa first, cementing the continent as the birthplace not just of humans, but of human behavior itself. And the earliest known Homo fossils, such as Homo habilis and Homo erectus, also cluster tightly in regions like Olduvai Gorge and Kubi Fora. Homo erectus would eventually be the first to leave the continent, but even that migrant species originated in Africa, reinforcing the pattern again and again. By the time we move toward modern humans, the genetic trail becomes even clearer. All living people today trace their mitochondrial DNA back to a population that lived in Africa roughly 150,000 to 200,000 years ago. This is not symbolic or metaphorical, it's biological proof stamped into our cells. The same applies to Y chromosome lineages, pointing to an African origin for paternal ancestry as well. No matter what angle you approach from, fossils, genetics, or ancient climate, the lines converge on the same continent. Yet the real mystery lies not in the fact that humans came from Africa, but why only Africa generated such profound transitions. And that is the quiet storm building beneath this narrative. The missing evidence suggesting that the continent's unique combination of instability, biodiversity, and geological drama was not just a backdrop, but the determining cause. As we leave this section and drift into the next, the story will move deeper into Africa's hidden climate engine and how its shifting rhythms forged our species from the ground up. The climate that shaped our earliest ancestors in Africa was not simply a backdrop, but a hidden engine, quietly turning the gears of evolution in ways so subtle and so relentless that it sculpted the destiny of every species that tried to survive there. As the Earth wobbled on its axis in long, rhythmic cycles known as Milankovitch cycles, Africa responded more dramatically than any other continent. Rainfall patterns didn't just shift mildly, they swung like a pendulum between lush green worlds and parched, desolate plains. This constant switching, occurring roughly every 20,000 to 40,000 years, meant that early hominins were never allowed to settle into a stable lifestyle. Instead, they lived on an ecological edge, where each generation had to adapt to a world that seemed familiar one decade and utterly transformed the next, creating exactly the kind of pressure that drives innovative behavior, diverse physiology, and ultimately new species. Mainstream research often simplifies this process by saying, Africa got drier over time, but the real story is far more intricate. Around 3 million years ago, when creatures like Australopithecus were navigating their precarious lives, Africa underwent a dramatic climatic reorganization. The once expansive forests began to splinter into mosaics of woodland and savanna. Rain belts moved north and south in response to small changes in Earth's orbital tilt, and vast lakes blinked in and out of existence like slow-motion mirages. Lake Turkana, for example, swelled to immense sizes during wet periods, then shrank into smaller fragments during dry spells. Every shift changed which animals lived nearby, which plants hominins could eat, and what dangers lurked in the tall grasses. These weren't gentle nudges. These were deep ecological pulses capable of altering survival strategies. Important facts connect directly to these cycles. It was during one of Africa's major drying phases, around 2.8 million years ago, that the earliest known Homo, the beginnings of our genus, appeared. The timing is striking. As the forests dwindled, the need to travel farther distances for food likely encouraged traits such as longer legs, more efficient bipedalism, and greater heat tolerance. The brain also began its long period of expansion, perhaps because individuals who could remember scattered food sources, track seasonal patterns, or communicate subtle warnings had the highest chance of surviving unpredictable climates. When Africa breathed in green abundance, hominin populations grew. When Africa exhaled dryness and scarcity, only the most adaptable individuals survived. Over thousands of generations, this selective squeezing produced profound changes. Real facts also show how Africa's climate extremes outpaced most other regions. The ice ages that gripped Europe and Asia came with long stretches of cold but relatively predictable cycles. Africa, by contrast, experienced climate flickering, rapid shifts between wet and dry conditions, sometimes within centuries. The East African Rift amplified these effects by channeling monsoon winds and intensifying rain shadows. Hominins living there had no choice. They had to become masters of flexibility or vanish. This hidden climate engine is now recognized as a major driving force behind the evolution of new species, especially in the hominin lineage. Imagine following an early hominin group through one of these sudden transitions. For several generations, their environment might be rich with fruiting trees, shaded paths, and plentiful fresh water. Infants would grow up learning the smells of wet soil, the patterns of leaves, and the calls of forest birds. But then the rainfall shifts. A dry wind sweeps across the land, rivers shrink and the lakes retreat, leaving cracked earth where water once shimmered. Trees wither and fall. Grass takes over. New predators, fast, silent, and built for open terrain, appear on the horizon. In just a few generations, everything that sustained their way of life disappears. For them to survive, they must change their diet, explore new territories, rely more heavily on cooperation, or risk extinction. This relentless pattern carved adaptive versatility deep into the hominin lineage, and that versatility set our ancestors apart long before they became fully human. Specific timelines map these transitions with eerie clarity. Around 1.8 million years ago, during a major dry phase, Homo erectus emerged with longer limbs, narrower hips, and bodies built for endurance walking and running, traits perfectly suited for life on sprawling savannas. Around 800,000 to 600,000 years ago, another climatic upheaval aligned with increases in brain volume and the appearance of more sophisticated Acheulean tools. And around 300,000 years ago, in an Africa divided by wet and dry pulses, the earliest Homo sapiens arose in regions like Jebel Irhoud. Each climatic pulse parallels a biological or cultural shift, as though evolution were responding to a metronome hidden in the sky. The missing evidence woven into this story comes from the brevity of wet periods. Lush phases encouraged population expansion, which allowed diversity and experimentation in behavior, perhaps early symbolic marks, complex group dynamics, or new dietary strategies. But when the continent dried again, many populations collapsed or relocated, leaving few traces behind. This explains why archaeologists find tantalizing hints: stone flakes, burned bones, pigment residues, embedded in layers of soil that appear only briefly before disappearing. Africa's climate engine erased as much as it created, washing away many early experiments before they could leave lasting fossil records. Another important fact: the expansion and contraction of green Sahara cycles. Multiple times over the past few million years, the Sahara transformed from deadly desert to lush grassland, filled with lakes, hippos, crocodiles, and even early human travelers. But each green period lasted only a short time before the desert returned, isolating populations again. These cycles shaped migration routes inside Africa, encouraging genetic mixing during wet periods and isolating groups during dry periods. Genetic studies today reflect these pulses, showing bursts of diversity followed by bottlenecks, all within Africa long before humans ever left it. In this way, Africa's climatic instability wasn't a barrier to human evolution, it was the forge. It rewarded adaptability, intelligence, cooperation, and curiosity. It punished rigidity and hesitation. And because the continent experienced these climatic beatings more intensely than anywhere else, only there could a species emerge capable of enduring the world's extremes. As this climate engine continues humming beneath our story, the narrative will soon shift into the geological forces that amplified its effects. The Rift Valley, The scar running through the continent did more than shape landscapes. It intensified climate swings, isolated populations, and created one of the most potent evolutionary laboratories on Earth. The African landscape did not simply challenge our ancestors with shifting climates. It rose, split, cracked, and reshaped itself beneath their feet, turning vast regions into a geological crucible where evolution accelerated in ways impossible anywhere else on Earth. The Great Rift Valley, stretching more than 6,000 kilometers from the Red Sea down to Mozambique, was not just a scar across the continent. It was the stage where countless hominin species emerged, adapted, and vanished. This immense fault system pulled the Earth's crust apart, forming towering escarpments, deep lakes, volcanic highlands, and fertile basins. And within these shifting zones of isolation and opportunity, early humans found themselves pressured into new forms, new abilities, and new minds. It is impossible to understand why human evolution happened only in Africa without understanding how the Rift Valley acted as evolution's furnace. Mainstream science often describes the Rift Valley as a region rich in fossils, but the truth runs deeper. The valley didn't merely preserve our ancestors, it created the conditions that produced them. When tectonic plates began pulling apart around 25 million years ago, the land fractured into a series of parallel ridges and troughs. This produced mosaics of habitats side by side, lush forests in one valley, open grasslands in the next, volcanic hills above, freshwater lakes below. Early hominins living in this region faced a constantly shifting patchwork of environments, each demanding different skills and adaptations. Species that could not adjust fast enough disappeared, while those with curiosity, flexibility, and resilience survived. This geographical fragmentation acted like nature's experiment board, where populations split, evolved independently, and sometimes reconnected, allowing traits to spread or perish. Real facts highlight this pattern with striking clarity. Australopithecus afarensis, known best from the famous Lucy, thrived in the rift around 3.5 million years ago, navigating a mixed environment of woodlands, floodplains, and open savannas. Their bones show adaptations for both climbing and walking, a dual capability shaped by landscapes that demanded versatility. Later species like Paranthropus boisei evolved powerful jaws and massive molars, perfectly suited for a diet of tough vegetation found in drier rift environments. In contrast, early Homo species developed more delicate facial structures and broader dietary flexibility, allowing them to exploit changing resources. These divergent adaptations underscore how different corners of the Rift Valley, sometimes only a few dozen kilometers apart, pushed hominin populations down dramatically different evolutionary paths. The valley didn't force a single direction, it created multiple routes and let natural selection decide which ones would endure. Volcanic activity played a central role in this evolutionary drama. Eruptions blanketed entire regions with layers of ash, killing wildlife yet offering unexpected gifts to future scientists. Ash layers acted like timestamps, allowing archaeologists to precisely date fossils and tools trapped beneath them. This is why sites such as Hadar, Kubifora, Olduvai Gorge, and Laetoli are so well studied. They lie within volcanic landscapes where ash preserved millions of years of hominin history. But beyond preservation, volcanic activity reshaped the environment in ways that forced rapid adaptation. New lava flows altered river paths and replaced fertile zones with barren rock. Earthquakes shifted water sources overnight. Lakes rose and fell in rhythm with tectonic pressures. These changes created evolutionary bottlenecks, moments where only the most adaptable populations survived, just as we see in the fossil record. Important facts reveal how these geological shifts align with major turning points in our lineage. Around 2.6 million years ago, the earliest stone tools appear near the Rift Valley. Their timing coincides with a period of intensified tectonic activity and climate fluctuations, suggesting that the challenges of acquiring new food sources pushed hominins to invent cutting tools. Not long after, around 2 million years ago, Homo erectus emerged with a larger brain, longer legs, and bodies adapted for endurance across vast distances. This evolutionary leap aligns with changes in the Rift Valley that expanded open savannas, encouraging long-distance travel and new hunting strategies. These correlations aren't coincidences. They show how geological instability shaped biological innovation. The rift also acted as a corridor and, at times, a barrier for movement. Lakes that expanded during wet periods isolated populations on peninsulas or islands, promoting genetic divergence. When lakes shrank again, these groups reconnected, allowing genes and ideas to spread. This back-and-forth cycle created bursts of diversity, followed by waves of blending, a process supported by genetic evidence showing complex population mixing in ancient Africa long before Homo sapiens appeared. The valley's shifting lakes, like the immense Paleo Lake Turkana, were not just water sources, they were architects of our genetic story. One of the most striking real facts is how the Rift Valley shaped brain evolution. Scientists now know that cognitive development is influenced by social complexity, dietary quality, and environmental unpredictability. All three factors were abundant in rift ecosystems. As hominin groups navigated terrain riddled with cliffs, predators, unstable resources, and sudden environmental change, individuals capable of planning, communicating, and forming stronger social bonds gained survival advantages. These pressures likely encouraged the spread of larger brains, more sophisticated cooperation, and early forms of culture. The rift wasn't simply a geographic feature, it was the training ground for intelligence. Even the missing evidence, the fossils yet to be found, points toward the rift. Because erosion constantly exposes new layers, every decade brings discoveries of transitional species that fill evolutionary gaps. Australopithecus anamensis, Australopithecus dearameda, Paranthropus ethiopicus, Homo rudolfensis, Homo naledi, all emerged from regions influenced by the rift. Many researchers believe that several key ancestors still lie hidden beneath sediment or volcanic ash, waiting to be uncovered. The fact that so many pivotal fossils appear in or around the rift is not random. It reflects the valley's unique capacity to generate, isolate, and preserve early humans. To understand the Rift Valley as an evolutionary crucible, imagine walking through it during a period of intense tectonic stretching. You would see towering walls of rock on either side, the smell of sulfur from distant volcanic vents, herds migrating across open plains, and clusters of trees hugging shrinking lakes. You might hear the distant crack of shifting rock or feel tremors underfoot. Rainfall would vary drastically from one valley to the next. A group of early humans living here would need to know every water source, every edible plant, every safe shelter, every predator track. They would need to communicate, remember, experiment, and adapt, skills that shaped us long before written history. This is why the Rift Valley is not merely a location, but a force, one that guided our evolution with invisible hands. As the valley widened and fractured, so did the paths our ancestors walked, each split leading toward new possibilities. And as the story glides forward, this geological crucible will connect naturally to the next layer of evidence, how small populations trapped within these shifting landscapes created the genetic bottlenecks that still echo in every human alive today. The trail of our ancestry narrows as we glide deeper into time, and by the moment we arrive at the genetic evidence, the story becomes startlingly intimate. Because now the clues aren't embedded in fossils or stone tools or ancient lake beds, but inside you, inside me, inside every living human. This evidence, quiet and mathematical, tells us something almost uncomfortable, that all modern humans descend from a surprisingly small population that lived only in Africa, and that at several points in our past, our numbers shrank so drastically that the entirety of humankind could have fit inside a small village. This, the genetic bottleneck trail, is not a metaphor but a real biological echo, stamped into mitochondrial DNA, Y chromosomes, and the billions of nucleotides that shape who we are. And the moment we follow those echoes backward, all paths collapse into the same continent, the same population, the same ancient African cradle. Mainstream science has long accepted that humans originated in Africa, but genetic studies revealed something more dramatic. Not only did we begin there, but we began from an incredibly restricted gene pool. Mitochondrial DNA, the tiny genetic circle passed from mother to child, traces all living humans back to a woman who lived roughly 150,000 to 200,000 years ago in Africa. She is not the only woman of her era, nor is she our only ancestor, but rather the last woman whose mitochondrial line survived unbroken to the present. Population geneticists call her mitochondrial Eve, and although her name is symbolic, the biological fact is not. Every mother alive today descends from her lineage. The same narrowing appears in paternal DNA. The Y chromosome inherited from father to son traces back to a man who lived roughly 200,000 to 300,000 years ago, also in Africa. His lineage persisted while countless others vanished. These genetic anchors, maternal and paternal, don't mark the first humans, but they mark the survivors of ancient bottlenecks. Their existence tells us that early Homo sapiens were not widespread thriving masses. They were small, vulnerable, clustered communities navigating a continent that could shift from paradise to scarcity in the span of a few centuries. But the real deeper fact emerges when we look at genome-wide data. Modern humans show extraordinarily low genetic diversity compared to other species. Chimpanzee populations in a single forest sometimes carry more genetic variation than the entire human species worldwide. That is not normal. That is the signature of bottlenecks, episodes when our ancestors nearly died out. The largest of these appears to have occurred between 70,000 and 100,000 years ago, reducing humanity to perhaps just a few thousand individuals. Some estimates suggest around 1 in 10,000 breeding adults. It is chilling to imagine a planet filled with animals, yet our entire species teetering on the edge of disappearance. Important facts link these bottlenecks to events occurring inside Africa, long before humans spread to Eurasia. Climate instability once again played a role. Around 120,000 years ago, Africa experienced cycles of severe drought that dried lakes, shrank rivers, and transformed fertile belts into barren expanses. Genetic evidence maps directly onto these drought periods. As water sources vanished, populations fragmented and shrank. Those that survived carried the few genetic lineages we still see today. Other populations, perhaps with rich cultures, tools, or symbolic practices, simply vanished without a trace. Their genes are gone, their stories erased. This explains one of the most puzzling truths: why Africa holds archaeological hints of early sophistication far older than similar evidence outside the continent, yet the genetic legacy of many early African groups seems truncated. Bottlenecks pruned our lineage again and again. Real facts also show how some bottlenecks created the foundation for later expansions. After each period of drought or ecological collapse, surviving populations regrouped around stable refugia, regions where water remained constant. These refugia may have formed around parts of East Africa, Southern Africa, and the African coasts. Genetic diversity today clusters around these regions, suggesting they served as the safe harbors of ancient humanity. In these havens, populations recovered, interbred, exchanged ideas, and, importantly, carried genetic variations tied to immunity, metabolism, brain development, and physical endurance. The diversity formed within Africa long before dispersal is far richer than what is found outside Africa, a fact mirrored in genomic studies. African populations today carry the highest genetic diversity in the world because they remained in the homeland of our species, where lineages split, blended, and persisted. The bottleneck trail also exposes a missing chapter: the existence of ancient African populations whose genetic traces barely survive. Some genomic signatures suggest that early Homo sapiens interbred with deeply divergent African groups, sometimes called ghost lineages, comparable to how later humans interbred with Neanderthals and Denisovans. These ghost populations likely lived in isolated pockets shaped by Rift Valley geography, shifting lakes, and climate pulses. Their DNA occasionally surfaces as small fragments in populations across West, Central, and Southern Africa. Their fossils may be buried in sediment we have not yet sifted. Their cultures may be lost. but their faint genetic fingerprints confirm they existed and played a role in shaping the humans who would eventually walk out of Africa. One important timeline stands out. By 300,000 years ago, early Homo sapiens had appeared in multiple regions across Africa: Jebel Irhoud in Morocco, Florisbad in South Africa, Omo Kibish and Herto in Ethiopia. Yet these groups were not identical. They were variations of an emerging species shaped by scattered refugia and recurring bottlenecks. This mosaic origin explains why early humans looked somewhat different depending on where they lived. But the genetic bottlenecks, especially the major one around 70,000 years ago, compressed these differences into a narrower, more unified lineage. The humans who eventually migrated out of Africa around 60,000 years ago carried only a fraction of the diversity present within Africa at that time. To understand the emotional weight of this, imagine walking through an African valley during one of these bottlenecks. The air is dry. Vegetation is sparse. A small band of humans travels from one shrinking waterhole to another, relying on ancestral knowledge passed down through generations. They watch the sky for storms that never come. They sharpen tools that feel increasingly heavy in weary hands. And yet, they share stories at night, quiet stories around small fires, stories that comfort them in the darkness. These were the people who survived. Their resilience allowed the human story to continue. All of us, every person alive today, descend from these handfuls of determined groups that kept walking, kept learning, kept adapting. The genetic bottleneck trail does more than prove our African origin. It explains why our species carries the traits we do: cooperation, adaptability, sensitivity to social bonds, and the psychological need for connection. Small populations constrained for generations evolve behaviors that prioritize group survival. Unity becomes strength. Memory becomes survival. Communication becomes lifeline. And as the bottleneck trail narrows to its final threads, it leads naturally toward an even stranger chapter: the vanished ancestor puzzle. Missing fossils that must exist somewhere beneath African soil, transitional species linking the earliest Homo to later humans, still waiting to be uncovered. The deeper we follow the ancient trail into Africa's past, the more we begin to sense a peculiar emptiness between the layers of evidence. A series of missing footprints in the sand where someone should have walked, a shadow of an ancestor that logic insists must have existed, but whose bones have not yet been found. This is the vanished ancestor puzzle, the quiet riddle sitting at the center of human evolution, hinting that an entire chapter of our origin story remains hidden beneath African sediment, undiscovered or perhaps erased by time. The fossils we do possess form a remarkable arc: Australopithecus, early Homo, archaic Homo sapiens. But there are gaps so large, transitions so abrupt, that it feels as though someone has removed key pages from a long, ancient book. And despite the richness of African fossil beds, the missing transitions keep pulling at the seams of the story, suggesting that evolution was more complex, more multi-branching, and more deeply rooted in Africa than we can fully see. Mainstream science acknowledges at least two major gaps. The first lies between Australopithecus species, around 4 to 2 million years ago, and the earliest members of our genus, Homo, appearing roughly 2.8 million years ago. The second gap stretches between early Homo species and the emergence of anatomically modern Homo sapiens more than 300,000 years ago. Both transitions contain stunning evolutionary leaps: larger brains, more human-like bodies, refined hands, and new behaviors that should have left behind a richer fossil trail. But the fossils we find are scattered, patchy, and often appear suddenly, as if a new species emerged out of nowhere. This suddenness is an illusion, of course. Evolution never works in jumps. But the missing intermediates imply that much of the story still lies buried beneath Africa's shifting landscapes, waiting. One real fact underscores the mystery. Before 2013, we had virtually no fossil evidence of Homo between 2 million and 3 million years ago. Then came a fragment of a jawbone from the Afar region of Ethiopia, dated to 2.8 million years. It bridged part of the gap, but only enough to deepen the question. Where are the forms that connect Australopithecus and Homo more completely? Where are the populations experimenting with early tool use, shifting diets, expanding social dynamics, changing proportions? These species must have existed because fossils like Australopithecus afarensis and Australopithecus africanus were not fully equipped to perform the behaviors seen in early Homo. Yet for now, these transitional hominins hover like ghosts in our evolutionary timeline. Important facts highlight the second great gap, the one leading to Homo sapiens. Around 700 to 400,000 years ago, Africa hosted archaic human species whose remains are sparse and often fragmented. These hominins, sometimes grouped under names like Homo heidelbergensis or Homo rhodesiensis, represent the immediate predecessors of our own species. Yet most of their fossils are partial skulls, fragments of jaws or isolated teeth. The Kabwe skull from Zambia, the Bodo cranium from Ethiopia, and the Saldanha remains from South Africa show a blend of older and newer traits, but they cannot form a continuous sequence because the fossil record is too thin. It is as though the lineage leading to Homo sapiens passed through a narrow doorway in time, shedding layers of diversity we have yet to recover. Real facts show how African environments contributed to this patchiness. Floods, shifts in lakes, volcanic eruptions, rapid erosion, and deep burial have destroyed or hidden countless fossils. Many African hominin habitats, like dense tropical forests, are hostile to fossilization. And even in excellent preservation regions like the Rift Valley, only a fraction of ancient landscapes remain accessible. Some fossils lie beneath hundreds of meters of sediment, others eroded away millions of years ago. This is why discoveries often happen suddenly, like windows briefly opening before closing again. The missing ancestor puzzle becomes even more intriguing when we observe fossils that don't fit neatly into known categories. Australopithecus sediba, discovered in South Africa, lived around 1.98 million years ago and shows a bizarrely human-like hand and pelvis paired with a primitive upper body. Its mixture of traits seems to bridge Australopithecus and Homo, yet its location in southern Africa raises the question, was southern Africa home to key transitional populations we haven't fully recognized? Similarly, the recently discovered Homo naledi, though much younger than expected, possesses a strangely mosaic anatomy, mixing primitive shoulders and fingers with more human-like legs and feet. These outlier species challenge the simple ladder model of evolution and support a more complex truth. Africa hosted multiple parallel lineages, some of which may have contributed to our ancestry, while others vanished without leaving genetic traces. The real important fact is this: human evolution in Africa was not a single lineage, but a braided river. Dozens of hominin species likely lived, interacted, competed, and occasionally interbred across the continent. Some lines branched and ended, some merged with others. Some may have contributed small genetic fragments to emerging human groups, and many species, perhaps most, left no fossils we've yet identified. The transition to Homo sapiens was not a straight ascent. It was a messy, intricate process shaped by isolation, climate swings, and migrations within Africa long before any humans left the continent. This missing evidence also hints at a more profound truth. Some key adaptations may have evolved in small, isolated populations whose fossils remain undiscovered. For example, the development of rounded skulls, reduced brow ridges, and reorganized brains, the hallmark features of Homo sapiens, appear in the fossil record somewhat abruptly around 300,000 years ago. Yet genetic evidence suggests these traits may have evolved gradually in scattered groups before spreading across Africa through interbreeding. This means the populations who first developed these defining characteristics may lie buried in regions we have barely explored, perhaps under forest floors in Central Africa, beneath dunes in the Sahara, or within deep sediment layers unreached by excavations. To imagine this vanished ancestor world, picture a landscape where multiple human-like species moved through the same valleys but lived in separate groups, some tall and slender, some small and robust, some with slightly different skull shapes, some with varying brain sizes. They gathered around waterholes, crafted tools from stone, and navigated dangers from predators. They likely observed one another from a distance, aware that their neighbors were similar yet different. Over tens of thousands of years, some groups would migrate and meet others, exchanging genes or technologies. Others would vanish quietly, leaving only a handful of bones or none at all. And this puzzle is not just an academic curiosity. It explains why the story of human evolution could only have unfolded in Africa. The continent's immense size, environmental diversity, and geological dynamism allowed dozens of evolutionary experiments to run simultaneously. Where Eurasia hosted only a few hominin species, Africa held many. Where other continents offered stability, Africa offered complexity. And out of this complexity came us. As the vanished ancestor puzzle fades into the horizon, the narrative will flow naturally into the next truth, that long before humans journeyed beyond Africa, they were already crafting tools, simple at first, then astonishingly sophisticated, tools that reveal how behavior evolved alongside biology, shaping what it meant to be human. Before a single human ancestor ever set foot outside Africa, long before migrations or contact with other continents, a quiet revolution unfolded on the savannas, lake shores, and river valleys of the continent, the invention and refinement of tools. These objects, simple yet transformative, marked the moment when early hominins began reshaping their environment instead of being shaped entirely by it. And the missing evidence becomes clearer here, because the earliest stone tools, the first sparks of technology, appear exclusively in Africa, rooted deeply in landscapes where no early humans had yet dispersed. This means that the story of technology, ingenuity, and behavioral evolution began not as a global phenomenon, but as a uniquely African one. Tools before travelers, ideas before migration, innovation before expansion. And behind this lies a profound truth. The development of tools was not an optional step, but the very engine that later made humanity capable of leaving Africa at all. Mainstream archaeology points to the Oldowan tool industry as the oldest widespread technological tradition, dated to around 2.6 million years ago at sites such as Gona and Katagona in Ethiopia. These tools, simple flakes struck from river cobbles, sharp-edged pieces used for cutting meat and plants, represent the earliest known example of hominins altering stone deliberately. But real facts complicate the story further. In 2015, scientists discovered even older tools at Lomekwi 3 in Kenya, unmistakably shaped by hominin hands and dated to 3 million years ago, predating the genus Homo entirely. This suggests that toolmaking didn't begin with humans, it began with Australopithecines, or their close relatives. And again, all these early tools emerge only in Africa, reinforcing the continent's role as the incubator of technological thought. Tools before travelers is not just a timeline, it's a pattern showing that early humans developed complex behavior while still deeply rooted in African ecosystems. For nearly 2 million years, advances in technology never correlated with migration out of the continent. Instead, hominins improved tools while remaining within Africa, refining their techniques in response to evolving climates and landscapes. Oldowan tools persisted for hundreds of thousands of years, shaping the diets and survival strategies of early Homo species, such as Homo habilis and Homo rudolfensis. These tools allowed early hominins to scavenge carcasses left by large predators, scrape marrow from bones, and access nutrient-rich fats and proteins that fueled brain growth. This dietary shift marks one of the most important steps in our evolution, yet it happened entirely in Africa, long before early humans ventured outwards. As climates shifted and grasslands expanded, tool-making evolved. Around 1.7 million years ago, the Acheulean industry emerged, characterized by elegant symmetrical hand axes crafted with impressive precision. These tools, found at African sites like Koki Saleh in Kenya, Konso in Ethiopia, and Olduvai Gorge in Tanzania, represent a leap not only in skill but in cognition. Making a hand axe required planning, spatial awareness, and fine motor control. It also required a mental blueprint, a level of abstract thinking far beyond anything seen in earlier species. The Acheulean tradition endured for more than 1 million years, but what matters most is its birthplace, Africa, and only Africa for hundreds of thousands of years before appearing elsewhere. This timeline proves that technological sophistication emerged slowly, methodically, and deeply entwined with African landscapes. Important facts reveal why innovation stayed rooted in Africa for so long. The continent's environments were diverse and harsh, demanding constant adaptation. Hominins moved between woodlands, grasslands, volcanic plains, and river deltas. Each ecosystem required new strategies and tools. Because populations often became isolated by shifting lakes or tectonic changes, different groups experimented independently. Some refined hand axes, others improved cutting flakes, still others used tools infrequently. The archaeological diversity across Africa, from the earliest Oldowan sites to the rich tool assemblages of the Middle Stone Age, reflects a continent filled with technological experiments, many of which were pruned by environmental challenges or replaced by superior designs. Real facts highlight the significance of later African innovations. By 300,000 years ago, long before humans left the continent, African Middle Stone Age populations developed tools far more complex than anything made by Neanderthals or Denisovans at that time. These included hafted spear points, pressure-flaked blades, bone tools, pigments, and perhaps even symbolic marks. The tools found at sites like Olorja Sile in Kenya, Pinnacle Point in South Africa, and Blombos Cave show that behavioral modernity, defined by planning, composite technologies, long-distance resource transport, and symbolic thinking, emerged in Africa first. These behaviors would later allow Homo sapiens to survive new climates, hunt different prey, and navigate unfamiliar landscapes during migrations. But their roots lie firmly within Africa's ancient soils. The missing evidence in tool history is as intriguing as the fossils. Many early tools were made from perishable materials, wood, fiber, bone, that did not survive. Stone tools are only one visible layer of an invisible technological world. Wooden spears found in Eurasia hint at an older African tradition of wooden weaponry that is simply decayed. Pigment residues found in African caves suggest early symbolic behavior that may have existed long before the earliest confirmed evidence. These missing pieces point toward a much older, richer, technological culture within Africa, one that fossilizes poorly but shaped the trajectory of human evolution long before migrations began. To imagine tools before travelers, picture a group of early Homo erectus gathered along the edge of a Rift Valley lake roughly 1.6 million years ago. The sun is low, casting long shadows across the volcanic plains. A small group crouches near a pile of riverstones, striking symmetrical hand axes with rhythmic taps. Sparks flicker in the fading light. A child watches, learning patiently. Nearby, others butcher a freshly scavenged antelope, using flakes to slice through muscle and skin. These early humans have no idea they are laying the foundation for humanity's future. They are simply surviving. But every tool they craft carves new possibilities into existence, shaping bodies, diets, and minds. These tools transformed relationships within hominin communities. Cooperation became more important because stone knapping required knowledge transfer, adults teaching children, experts demonstrating techniques, and groups sharing resources. Communication became more refined because planning a hunt or coordinating a butchering effort required more than gestures. Social bonds deepened because survival depended increasingly on shared skills and collective memory. Again, all of this unfolded entirely inside Africa before any hominin left the continent permanently. The continent's technological legacy shapes every later chapter of the human story. Without stone tools, early Homo species could not have adapted to new diets. Without new diets, brains could not have enlarged. Without enlarged brains, symbolic thought could not emerge. Without symbolic thought, the migrations that shaped global humanity could never have occurred. Africa was not merely the starting point, it was the training ground, the workshop, the laboratory of human ingenuity. And as we glide from this world of stone and skill, the narrative naturally turns toward another transformative innovation that emerged long before humans walked into Eurasia. The taming of fire, a quiet force that reshaped physiology, cognition, and the human rhythm of life. Fire did not appear to our ancestors as a dramatic revelation, nor as a single moment of sudden mastery. Instead, it emerged slowly, tentatively, in the shifting African night, a soft glow beyond the tall grass, a flicker of warmth in a dark world filled with predators. And yet, this faint trembling force became one of the most transformative technologies in human evolution. The earliest experiments with fire happened exclusively in Africa, long before migration, long before complex tools, long before art or ritual. These early Africans, our distant ancestors, were the first creatures to borrow a piece of the sun, to tame it, to shape it, and to let it shape them in return. If tools marked the beginning of human intention, fire marked the beginning of human transformation. Mainstream science agrees that the earliest use of fire by hominins comes from African sites more than 1 million years old. At Wonderwork Cave in South Africa, archaeologists uncovered burned plant ash and charred bone fragments dating to around 1 million years ago, showing controlled fire rather than natural wildfire deposits. At Kubifora in Kenya, sediments contain burnt patches from roughly 1.5 million years ago, hinting at early fire interaction. These early fires are not hearths as we know them, not cozy circular pits where families sat and shared meals, but scattered signs that hominins were learning to manage flame, protect embers, and perhaps carry smoldering wood from one place to another. Real facts push the timeline even further. Some scientists believe early Homo erectus may have begun interacting with fire as far back as 1.7 million years ago, based on heat-treated stone and charred organic materials found in East African sediments. If true, this would mean fire accompanied Homo erectus as it slowly expanded within Africa long before leaving the continent. Importantly, however, none of the earliest fire use evidence occurs outside Africa until much later, another sign that Africa was the only continent fostering major evolutionary innovations at this early stage. But the real transformation began not with how fire was used, but with how fire changed bodies. Cooking, one of the most important facts in human evolution, did not merely soften food. It altered digestive systems, reduced chewing time, increased caloric availability, and fundamentally changed the energy economy of our species. This idea, supported by the cooking hypothesis, suggests that cooked food allowed early humans to extract far more energy from plants and meat, freeing up metabolic resources for brain growth. The earliest robust evidence for habitual cooking appears around 800,000 to 900,000 years ago, and these signs also come exclusively from African sites. If cooking began in Africa, then so did the physiological shift that allowed our brains to expand to their modern sizes. To appreciate how dramatic this change was, consider the difference between a raw tuber and a cooked one. Early humans relying on raw plants would need to spend hours chewing every day, similar to chimpanzees. But cooking turns tough fiber into soft nourishment, releasing nutrients rapidly. In this sense, fire was not simply a tool, it was a digestive revolution. It meant shorter guts, smaller teeth, lighter jaws, and an evolutionary redirection of energy toward the brain. The impact reverberates even today. Our teeth, our stomachs, our metabolism all carry the legacy of African fires lit nearly 1 million years ago. Fire also changed behavior in profound ways. Before fire, night belonged to predators, lions, hyenas, leopards. Hominins spent nights in trees, caves, or fearfully huddled together. Fire extended daylight, pushing back the border of darkness. Around these early flames, social life changed. Individuals could gather safely, communicate, groom, plan tomorrow's movements, and share food without fear. These nighttime gatherings fostered deeper bonds, reinforced cooperation, and likely shaped the emotional rhythms of early humans. The flickering firelight became a teacher. It taught patience, story sharing, the passing of knowledge, and perhaps the first sense of home. Once again, the missing evidence is not in contradiction, but in absence. We know early fire use must have been common in Africa because of the scale of transformation it produced. Yet, definitive hearths are rare because fire leaves faint archaeological traces. Wind scatters ash. Rain washes away charcoal. Shifting sediments bury or erase evidence. Many ancient campsites in Africa may lie hidden beneath explosive volcanic layers or under deep deposits in caves. The earliest hearth that we haven't found is almost certainly older than the ones we have. The quiet story of fire's origins is undoubtedly rich, but only fragments have survived. Important facts illustrate how fire altered hunting and diet. Heat-treated stone tools found in South African Middle Stone Age sites, such as at Pinnacle Point, show that by around 160,000 years ago, Homo sapiens were using fire to improve tool quality. This means fire had become integrated into technological systems. Burned bones from multiple African sites, showing cut marks and heat patterns, reveal hominins roasting meat as early as 800,000 years ago. Cooking increased safety, killing parasites, and allowed early humans to eat foods like marrow, shellfish, roots, and tubers more efficiently. Fire also enabled the trend toward omnivory, giving our ancestors resilience against climate swings. Whether wet or dry, hot or cold, cooked food kept communities alive. Another real fact: fire made sleep safer. Hominins who could sleep on the ground, protected by fire, needed less time in arboreal shelters. This improved rest may have shaped brain function, memory consolidation, and the ability to learn complex tool-making sequences. In this sense, fire shaped not only the body but the mind. To imagine early firelight in Africa, picture a group of Homo erectus gathered under a darkening sky. They kneel beside a small fire, its glow flickering on their faces. Sparks drift upward like tiny stars. A carcass lies nearby, half butchered, waiting for roasting. Some individuals sit close for warmth, others scan the shadows for predators kept at bay by the flame. The night is quiet, except for crackling wood and murmured communication. These people do not yet grasp the cosmic significance of their actions, but they are laying the foundation for everything that will come. Over thousands of years, fire became more than a survival tool. It became a social anchor. It shaped rhythms of life, gathering at dusk, resting in warmth, waking to embers. Every culture on Earth still carries a remnant of this ancient pattern. Fire eventually fueled migration, allowing humans to survive colder climates. But before migration came mastery, and mastery happened in Africa alone. As the fire burns softly through this section, warming the edges of ancient nights, the story will soon transition toward another remarkable African phenomenon: the great acceleration of the human brain, a growth spurt that transformed clever hominins into something far more singular. The story of humanity narrows again as we step into one of the most extraordinary transitions in our entire evolutionary history. A moment when the human brain, after millions of years of slow and steady change, suddenly began to accelerate in size and complexity with a speed unmatched in the animal kingdom. This was not a global event. It was not a phenomenon shared across continents. It was an African transformation, a deep internal reshaping of minds that unfolded entirely within the continent, long before humans ever walked into Europe or Asia. The Great Brain Acceleration is one of the clearest signatures that our evolution happened only in Africa, because the forces that triggered it existed nowhere else. Intense climatic instability, diverse ecosystems, shifting habitats, and the social demands of increasingly complex hominin communities all collided to produce minds capable of planning, imagining, cooperating, and eventually dreaming. This section glides through that transformation, tracing how our ancestors' brains expanded and reorganized in response to African pressures that no other continent could replicate. Mainstream data tells us that around 2 million years ago, Homo erectus appeared with a brain size averaging 600,000 to 750 cubic centimeters, already larger than earlier Homo species. But over the next 1.5 million years, within Africa, the brain did something extraordinary. It nearly doubled. By 600,000 years ago, archaic humans such as Homo heidelbergensis in Africa possessed brains reaching 1,200 cubic centimeters, approaching the modern human average. And by 300,000 years ago, the earliest Homo sapiens skulls from Jebel Irhoud in Morocco reveal brains almost identical in volume to ours, even if their shape had not yet fully rounded. These leaps did not occur in Eurasia first. They happened in Africa, and they happened repeatedly, with each phase aligned to specific environmental and social pressures. One important fact stands out: the dramatic pulses of brain growth align closely with African climate swings. During periods when rainfall shifted, habitats fragmented, and food sources became unpredictable, hominin groups had to innovate or perish. In times of scarcity, individuals who could remember distant waterholes, plan movements, track seasons, coordinate hunts, or manipulate tools had higher survival odds. This constant selection for adaptability, memory, and foresight shaped the brain long before symbolic thought emerged. Africa's climate never allowed complacency. It demanded creativity. In this sense, the continent acted as a neurological forge, sharpening cognition generation after generation. Real facts tie physiological changes directly to these cognitive leaps. The shift toward cooked food, beginning around 800,000 and 900,000 years ago, freed metabolic energy that had once been consumed by digestion. Cooking softened foods and increased caloric efficiency, allowing early humans to devote more energy to maintaining and expanding brain tissue, an extremely costly organ. Social complexity compounded this effect. Larger brains allowed more intricate cooperation, which in turn required even greater cognitive resources. Evolution fed back on itself, with social and dietary pressures creating a spiral upward toward greater intelligence. Every step of this spiral occurred in Africa first. Another important factor in this brain acceleration was the expanding social world of early hominins. As groups grew larger and interacted more regularly, individuals needed to track relationships, understand emotions, anticipate actions, and maintain alliances. This type of cognition, often called social intelligence, is far more demanding than solving physical problems. It requires empathy, memory, and sophisticated communication. Fossil evidence suggests that early African hominins lived in increasingly cooperative communities, sharing tasks such as child-rearing, hunting, and foraging. Cooperation rewarded those who could interpret subtle cues, negotiate conflicts, and coordinate group actions. In this way, Africa's social landscapes became as important as its physical ones in shaping our expanding minds. The archaeological record offers glimpses of this cognitive complexity. The Acheulean hand axes crafted by Homo erectus, dating back to 1.7 million years ago, display symmetry and design principles that imply advanced planning. These tools were not random flakes. They were intentionally shaped, often far from where the raw stone was collected, showing foresight and mobility. Later tool industries from the African Middle Stone Age, such as those found at Kapthurin and Olorgesailie, include meticulously crafted points, blades, and pigment processing tools that reflect innovation, teaching, and long-term planning. These technological signatures mirror the internal changes unfolding in the hominin brain. Real facts reveal that Africa was not home to one ancestral population during these brain expansions, but many. Africa's immense size and ecological diversity allowed populations to evolve semi-independently. Some groups inhabited coastal regions rich in shellfish. Others lived in grasslands with large herbivore populations. Still others occupied forests or highland plateaus. Each environment applied different selective pressures, shaping cognitive variations that later blended together through migration and interbreeding. This mosaic approach, where multiple African lineages contributed to the final form of Homo sapiens, helps explain why modern humans display such remarkable neurological flexibility. Our brains were shaped by many ecosystems and not one. Another real intriguing fact: early Homo sapiens did not immediately possess the rounded globular brain shape characteristic of modern humans. Jebel Irhoud fossils show elongated skulls with large brain volumes, but not the reorganized internal architecture seen today. This suggests that after brain size reached modern levels, Africa continued shaping brain structure. Over the next 200,000 years, neural regions involved in social cognition, symbolic thinking, and language underwent refinement. This process appears tied to increased cooperation, early symbolic behaviors, pigment use, and long-distance transport of materials, all documented in African sites tens of thousands of years before appearing anywhere else. The missing evidence again whispers beneath this story. Many hominin species that contributed to cognitive evolution remain undocumented. Genetic signatures show that ancient African populations sometimes contributed small genetic fragments to modern humans, suggesting interbreeding with ghost lineages. These lineages likely carried cognitive innovations not preserved in the fossil record. Some may have possessed regional adaptations to droughts, forests, or hunting strategies. Their brains, though wiped from the world physically, live on in small genetic traces woven into modern African populations. This hidden inheritance reminds us that cognition was not shaped by a single species alone, but by a network of ancient hominins evolving together on African soil. To visualize this acceleration, imagine an African plain 800,000 years ago. A group of archaic humans gathers at a lakeshore during a brief wet phase. They communicate subtly, gestures, murmurs, shared glances, as they coordinate a hunt for grazing antelope. One individual uses a newly shaped spear point hafted to a wooden shaft with plant resin, a technique learned through hours of practice and demonstration. Another keeps track of the herd's movement, predicting where the animals will run. Later that night, around a fire that warms the cool air, they share roasted meat, communicate stories of the day, and teach younger members how to nap stone. Their brains are not yet ours, but they are unmistakably on the path, expanding, reorganizing, connecting ideas in new ways. What emerges from this story is unmistakable. The great acceleration of the human brain was not a global phenomenon. It was an African phenomenon, triggered by African climates, African landscapes, African social pressures, and African technologies. The mind that would later create language, art, and civilization was forged here, shaped by the continent long before migration. And as this section settles gently, the story moves toward another uniquely African challenge: surviving in a land filled with mega-predators where hominins had to become not only intelligent, but vigilant, cooperative, and daring to endure. Africa was not only a cradle of origins and a forge of intelligence, it was a continent alive with enormous, deadly creatures that stalked every shadow and waterhole, each one capable of ending the life of an early human in an instant. Before Homo sapiens, before long spears, before strategic hunting, hominins lived beside giant predators unmatched in ferocity: saber-toothed cats, massive hyenas, giant crocodiles, hunting lions twice the size of modern ones, and packs of predators that roamed open plains in numbers that would terrify any modern traveler. Survival in Africa required more than strength. It demanded cleverness, cooperation, awareness, and social unity. This section reveals how the presence of mega-predators shaped human evolution in ways no other continent could replicate. Why Africa's deadly ecological pressures forced our ancestors to become strategic, communicative, and deeply cooperative beings. The continent's predators didn't merely threaten hominins, they sculpted them. Mainstream paleoecology confirms that between 3 million and 200,000 years ago, Africa held one of the most dangerous predator guilds in Earth's history. Saber-toothed species such as Megantherion and Homotherium hunted with powerful forelimbs and long, slicing canines. Gigantic hyenas like Pachyrhina brevirostris weighed over 200 kilograms, capable of crushing bones thicker than a human femur. Enormous crocodiles, such as Crocodylus thorbjarnarsoni, an ancient species that could grow over 7 meters long, waded in rivers where early humans gathered to drink or fish. Even herbivores were deadly: giant buffalo with meter-long horns, aggressive hippos with massive jaws, and armored rhinoceroses shaped the daily danger around water sources. Real facts reveal an uncomfortable truth. Hominins were not apex predators for most of their evolutionary history. They were prey. Numerous hominin fossils show bite marks from saber-toothed cats, puncture wounds from large cats' canines, or crushing damage consistent with ancient hyenas. At the famous site of Swartkrans in South Africa, nearly a third of early hominin fossils show signs of predation. This means that survival required constant vigilance, group defense, and an acute awareness of the environment, traits that would feed directly into the evolution of intelligence and cooperation. This is where the important facts link closely to cognition. Living among predators forced hominins to develop sophisticated alarm calls, coordinated evasion strategies, and group cohesion. Predator pressure may have been one of the early drivers of vocal complexity, proto-language emerging not from abstract thought, but from the immediate necessity to warn others of danger. Early hominins likely used different alarm calls for big cats, snakes, and crocodiles, much like modern vervet monkeys do. Over time, these vocalizations may have evolved into more flexible communication, eventually laying groundwork for symbolic language. Africa's predators pushed communication forward. Megapredators also shaped the evolution of technology. Early stone tools were not only for cutting meat, they were for defense. Sharp flakes offered a last-ditch weapon against attackers. Later, Acheulean hand axes, though primarily used for butchering and processing plants, could serve as intimidating deterrents when brandished at predators. By 500,000 years ago, some African populations began using fire deliberately to ward off animals during the night. Fire kept lions away, deterred hyenas, and allowed hominins to sleep safely on the ground. Surviving alongside predators forced early humans to master fire earlier and rely on it more heavily than hominins in Eurasia, where large carnivores were fewer and environments less dangerous. One striking real fact: Homo erectus appears to have engaged in systematic scavenging and eventually coordinated hunting in regions filled with predators. At sites like Olorgesailie in Kenya, stone tools lie alongside carcasses of large mammals with cut marks layered over predator bite marks. This suggests hominins were bold enough to approach lion or hyena kills after the predator left briefly, or even to confront predators directly. Such behavior required exceptional courage and cooperation. A lone hominin would have been torn apart, but a group acting in unison could drive predators away through noise, fire, and sheer numbers. Over generations, fear turned into strategy. Strategy turned into coordinated action, and coordinated action became a cognitive habit. Another important fact: Africa's predator pressure forced hominins to develop long-term planning. Moving across the savanna meant knowing where predators hunted at different times of day. Groups learned safe migration routes, maintained knowledge of distant shelters, and developed patterns of scanning the landscape from elevated positions. This constant vigilance reshaped attention systems in the brain, making early humans exceptionally sensitive to movement, sound, and social cues. You can still see this legacy today. Humans are uniquely good at recognizing faces, scanning environments, and detecting danger even in peripheral vision. These traits are evolutionary gifts from a time when predators stalked every horizon. Living with predators also shaped the emotional world of early humans. Cooperation became emotionally rewarding because group cohesion determined survival. Empathy strengthened bonds between individuals. Attachment between mothers and children became deeper because wandering off alone was fatal. Community became an evolutionary necessity. The psychology of belonging, the sense that one survives better with others, was born in Africa under the shadow of predatory teeth. Predators also influenced settlement patterns. Fossil evidence shows that early hominins often positioned camps near cliff edges, rock shelters, or elevated viewpoints where they could watch for approaching threats. Waterholes were approached cautiously, often at dawn or dusk and always in groups. These habits, passed down over generations, shaped early culture. Knowledge of predator behavior became cultural memory, lessons taught through gesture, early speech, and nightly stories around the fire. The origins of storytelling itself may lie in these moments. Ancient humans recounting encounters with lions or hyenas, teaching the young how to recognize danger, how to move silently, how to avoid becoming prey. Real evidence shows that by 300 years ago, early Homo sapiens engaged in hunting strategies that surpassed predator behavior. They learned to track game over long distances, outmaneuvering big cats through endurance and cooperation. This ability, persistence hunting, was uniquely human and heavily shaped by Africa's heat and terrain. Humans could chase prey for hours until the animal collapsed from exhaustion, something no predator could accomplish. The hunted became hunters, but only after millions of years of surviving as prey. Still, the memories embedded in our biology remained. Our startle response, our fear of the dark, our anxiety around unseen movement, and our group bonding instincts all echo those ancient African nights where danger lurked just beyond the glow of the fire. To imagine this world, picture a group of early Homo erectus walking across an African plain at dusk. They carry stone tools and embers wrapped in bark. They move silently, eyes scanning the horizon. In the distance, a pride of ancient lions stirs. The humans adjust course without a word. They know the lion's patterns. They know the trees where leopards hide, the river bend where crocodiles wait, the caves where hyenas return with bones. Their minds carry maps of danger passed down through generations. This knowledge is not written, it is lived, it is survival. And as we step gently into the next phase of the story, this heightened vigilance and cooperation flows naturally into a new evolutionary leap, the emergence of complex speech, shaped first by danger, then by social unity, and finally by the need to share knowledge across generations, another innovation that began only in Africa. Long before humans carried language across deserts, mountains, and oceans, the earliest sparks of speech flickered quietly in the African night. It did not begin as poetry or stories or names for the stars. It began as warnings, sharp exhalations in the dark to signal a stalking leopard, subtle clicks to coordinate movement through tall grass, low murmurs to reassure infants pressed against their mothers' chests. In Africa, where predators prowled near every waterhole and survival depended on cooperation, the pressure to communicate grew stronger than in any other continent. And over hundreds of thousands of years, those pressures sculpted the earliest foundations of human speech. Africa did not just give rise to our species, it gave rise to our voices, our ability to shape breath into meaning, to transmit ideas across time, and to bind communities together through sound. Mainstream linguistic theory holds that complex language likely emerged between 100,000 and 300,000 years ago, but the roots run much deeper, entwined with the anatomy and behavior of earlier hominins. Fossil evidence suggests that even by 1.8 million years ago, Homo erectus possessed a spinal canal large enough to support the breath control required for basic vocalizations. Later species, such as Homo heidelbergensis, show anatomical features, expanded thoracic regions, refined motor control, and more human-like hyoid bones that hint at more sophisticated communication. While these beings did not speak as we do, they almost certainly used rich vocal repertoires, combining sounds with gestures, facial expressions, and social cues. Real facts from African Middle Stone Age archaeological sites point to symbolic thinking long before fully modern speech. At Blombos Cave in South Africa, pieces of ochre engraved with deliberate geometric patterns dating to around 75,000 years ago suggest early humans were capable of abstract thought, a cognitive foundation necessary for language. Similarly, beads made from Nassarius shells found at Taferalt, Morocco, and Pinnacle Point, South Africa, show early expressions of identity, status, and social meaning. These symbolic artifacts imply that early Homo sapiens were communicating concepts far more complex than simple survival cues. But the true pressure for the evolution of speech came from Africa's ecology. Important facts reveal that long-term survival required group coordination on a scale unmatched by other hominins. Persistence hunting, tracking an animal for hours under the sun, demanded constant communication. Cooperative child-rearing required the sharing of information between generations. Predator avoidance necessitated rapid, nuanced warnings tailored to different species. These pressures pushed vocal communication beyond simple calls. They encouraged variation, flexibility, and intentionality. One real striking piece of evidence comes from the click consonants found in several modern African languages, especially those spoken by Khoisan populations. Many linguists believe clicks may represent some of the oldest surviving phonemes in human speech, possibly dating back to early Homo sapiens populations in southern Africa. If true, this would mean that some of the earliest sounds, shaped by human tongues, still echo today in living communities, a linguistic fossil carried in breath instead of stone. The evolution of speech also involved dramatic changes in brain structure. As Africa's climate fluctuated and hominin groups split, migrated, and reunited across the continent, the cognitive demand for memory, narrative, and teaching increased. Parents passed survival strategies to children: how to nap stone, how to track antelope, how to recognize edible roots, how to predict seasonal rains. Complex knowledge couldn't be transmitted through simple gestures alone. Spoken language allowed communities to compress experience into teaching. This teaching expanded social networks, which in turn required even more linguistic capability, a self-amplifying evolutionary loop that took place entirely within Africa. An important fact from anatomy reinforces this timeline. The modern human hyoid bone found at Herto in Ethiopia, around 160,000 years old, is nearly identical to ours, suggesting the vocal tract capable of producing a wide range of sounds existed long before humans dispersed. Combined with evidence of symbolic practices and long-distance trade within Africa before migration, the picture becomes clear. The cognitive and anatomical equipment for language arose before humans left Africa. Eurasian populations later inherited these abilities fully formed. The missing evidence, though not contradictory, leaves tantalizing hints. It is likely that many early speech-like behaviors left no archaeological trace. Songs hummed at dusk, rhythmic chants during cooperative tasks, soothing tones used to calm a restless child. These ephemeral sounds vanished into the air, unrecorded. Researchers suspect that early humans developed proto-grammatical structures, ordering sounds to indicate direction, time, or intention, long before modern grammar emerged. These structures would have carried subtle variations, passing through countless African populations shaped by diverse environments. As languages evolved and diverged, some vanished forever, their richness lost long before humans encountered writing. To imagine the earliest sparks of speech, picture a small group of archaic Homo sapiens gathered around a dim fire in what is now southern Africa, roughly 150,000 years ago. Children sit close to the warmth while adults carve stone points. Soft voices fill the air, clicks, tones, murmurs, rising and falling in the rhythm of early language. One elder explains where to find fresh shellfish when the tide shifts. Another warns about a new pride of lions roaming near a river bend. A parent comforts an anxious child with a soothing sequence of sounds recognizable as a proto-lullaby. These sounds are not yet the languages we know, but they carry structure, emotion, intention. They are the roots of speech. Speech also reshaped social life, expanding trust and cooperation. With language, early humans could negotiate alliances, resolve conflicts, and coordinate hunts far more efficiently. They could express gratitude, grief, hope, and fear, forming deeper emotional bonds. Over time, storytelling emerged, turning memory into oral tradition. Stories taught moral lessons, preserved knowledge of landscapes, and bound groups together through shared identity. All of this began in Africa before the diaspora. Important facts indicate that by 70,000 years ago, the cognitive foundations of modern language were widespread across African Homo sapiens populations. When humans finally migrated into Arabia and beyond, they carried not only the physical traits of our species, but the linguistic foundations that would eventually blossom into thousands of languages worldwide. Africa's ecological and social pressures forged communication not as ornament, but as necessity. Language evolved because it was essential for survival in a world filled with predators, climatic uncertainty, and highly cooperative communities. And because these pressures were uniquely African, the earliest chapters of human speech could have unfolded nowhere else. As this section quiets its voice, the story turns toward geography, how Africa's vastness and natural barriers created long periods of isolation, shaping distinct human lineages across the continent before any journey outward began. Africa's landscapes were not simply vast, they were partitioned by mountains, deserts, forests, rift valleys, shifting lakes, and ancient rivers that rose and fell over millennia, creating long arcs of isolation between hominin populations. This isolation, stretching across hundreds of thousands of years, shaped the genetic and cultural diversity of ancient humans long before any migration out of the continent could occur. It is here, in the long isolation, that we understand why evolution happened only in Africa and not elsewhere. No other continent created such a deep mosaic of separated habitats, each one molding hominin populations differently, each one encouraging bursts of innovation, divergence, and experimentation. Africa was not a single cradle, but many cradles stitched together by shifting ecological borders that often closed for tens of thousands of years before opening briefly to allow mixing. This slow rhythm of division and reunion plays a crucial role in our story. Mainstream paleoanthropology now recognizes that early Homo sapiens did not arise from one location in Africa, but from multiple semi-isolated populations interacting over vast timescales. Genetic research supports this multi-regional African model, showing that early human groups across the continent diverged, evolved slightly differently, and then blended again through migration corridors. Around 300,000 years ago, when early Homo sapiens were emerging, Africa looked less like a continuous habitat and more like a patchwork of refugees. Northern Africa, impacted by Sahara expansions and contractions, Eastern Africa, shaped by Rift Valley tectonics, Southern Africa, buffered by coastal climates, and Central Africa, dense with rainforests. Each region created unique selective pressures. Real facts reveal that climatic shifts repeatedly closed these regions off from one another. For instance, the Sahara Desert expanded during dry periods into a massive, impassable barrier separating north from sub-Saharan populations. During wet phases, the Sahara transformed into a green expanse filled with lakes, grasslands, and abundant wildlife, enabling populations to reconnect. These cycles occurred dozens of times over the last million years, each one influencing population movement and genetic exchange. When the Sahara was dry, northern and sub-Saharan groups evolved in isolation. When it was wet, they interbred, sharing innovations, genes, and cultural practices. The rhythm of openness and closure shaped Homo sapiens long before we dispersed outward. The Rift Valley also contributed to this isolation. Its immense lakes, Turkana, Malawi, Tanganyika, expanded and contracted dramatically in response to rainfall shifts. When lakes expanded, they cut hominin populations into separate islands of evolution. When they receded, they reconnected territories. Archaeological evidence from regions like Lake Turkana shows dramatic swings in sediment layers, wet, rich layers full of aquatic life alternating with dry phases marked by wind-blown sand. These fluctuations created evolutionary islands, shaping groups differently even over relatively short distances. Important facts highlight how this isolation influenced human anatomy and culture. Fossils from different African regions during the emergence of Homo sapiens show variations in facial structure, cranial shape, and robustness. Individuals from Jebel Irhoud had elongated skulls, while early fossils from Omo Kibish and Herto in Ethiopia had more rounded cranial vaults. Southern African fossils display their own anatomical traits, yet all fall within the broader spectrum of early Homo sapiens. These differences are signs of populations evolving semi-independently before blending into a more unified lineage through later migrations within Africa. The long isolation also shaped technological traditions. African Middle Stone Age tool industries were not uniform. Instead, they varied widely across the continent. Eastern African populations produced finely retouched points and blades at sites like Gatamata. Southern African groups developed heat-treated stone tools and advanced pigment technologies at Pinnacle Point. Northern African populations created their own tool traditions along the coast and inland oases. These regional cultures persisted for tens of thousands of years before blending or being replaced, creating layers of innovation that only Africa's size and isolation could maintain. Real genetic facts deepen this story further. Studies show that some African populations diverged more than 200,000 years ago, remaining separate for tens of thousands of years before interbreeding again. Some lineages, such as those found in the genetic ancestry of hunter-gatherer groups in southern Africa, carry some of the oldest known branches of human DNA. Others, like the ancestors of some West and Central African populations, show admixture from ghost lineages, now extinct human groups not yet identified in the fossil record. Such complexity suggests a continent teeming with human diversity long before any diaspora. The missing evidence here is not surprising. Many regions that hosted isolated populations are now jungles, deserts, or deeply buried sediments. Rainforests, in particular, are poor at preserving fossils. Entire chapters of human prehistory may lie in Central Africa, a region underexplored due to environmental challenges. Similarly, the Sahara, once filled with rivers, lakes, and hominin populations, is today one of the least accessible archaeological regions in the world. Beneath its dunes lie ancient lakeshores, where humans once lived, crafted tools, tended hearths, and perhaps performed early rituals. These stories remain locked beneath shifting sands. To feel the emotional weight of Africa's long isolation, imagine standing at the edge of a Rift Valley lake 200,000 years ago. The water stretches to the horizon, dividing your small community from another group living on the far shore. The lake is too deep to cross. You know nothing of them except the distant glimmers of firelight at night. Your people have their own methods of napping stone, their own systems of sharing food, their own patterns of movement tied to seasonal rains. Across the lake, the other group lives with different strategies, different challenges, different stories. For thousands of years, these two groups never meet. They evolve separately, they change, they become distinct. And then, one day, perhaps thousands of years later, the lake recedes. Footpaths emerge from the mud. The two communities meet. Genes blend. Knowledge spreads. New innovations arise. This cycle repeats countless times across Africa. Isolation shaped human minds as much as it shaped bodies. Groups developed unique accents, communication styles, social structures, and rituals. When populations finally met after long separations, cultural exchange likely sparked bursts of creativity. New tool types, new symbols, new ideas. Diversity became strength, and Africa, with its vastness and isolation, became a generator of endless variation. This long isolation explains why Africa holds more human genetic diversity today than the rest of the world combined. Populations that remained within Africa retained ancient variation, while those that left carried with them only a small subset. This is why, paradoxically, non-African populations are genetically more similar to each other. They descend from fewer ancestral groups. As this section gently closes, the narrative shifts toward the crucial turning point, the moment when shifting climates finally opened a corridor out of Africa, allowing early humans, shaped by millions of years of African isolation, to step into the wider world for the first time. The moment when humans finally stepped beyond Africa was not a triumphant exodus, not a single march across a narrow land bridge, nor a sudden burst of exploration. It was a gradual, hesitant movement shaped by thousands of years of shifting rainbelts, shrinking deserts, and fleeting ecological corridors that opened and closed like slow-moving doors. For most of human history, Africa held us close, not by force, but by the simple reality that the world beyond was inhospitable, dry, cold, or empty of the resources our ancestors depended on. Only when the climate shifted in just the right way did a pathway emerge. This is the out of Africa threshold, the critical turning point when the same climate engine that forged us finally allowed us to leave. Mainstream paleoanthropology describes the major dispersal of Homo sapiens around 60,000 to 70,000 years ago, when small groups crossed out of northeastern Africa, possibly through the Bab el-Mandeb Strait or across the Sinai Peninsula. But the real story is far more layered. Evidence now shows that earlier waves of humans left Africa long before this, some as early as 130,000 years ago, others around 100,000 years ago, yet these early migrants either died out or were absorbed by later populations. Africa remained the central home of humanity throughout these earlier movements. The successful migration that populated the rest of the world was the final outcome of many failed attempts. Real facts show why migration was so difficult. For much of the last 300,000 years, the Sahara Desert acted as a massive wall. During dry phases, it expanded into an ocean of dunes, making northward travel nearly impossible for hunter-gatherers dependent on consistent water sources. To the northeast, deserts and mountains blocked movement into the Levant, except during brief humid intervals. To the east, the Red Sea narrowed and widened in response to sea level changes. Sometimes it was a treacherous barrier, sometimes a narrow crossing. These geographic obstacles meant that climate, not curiosity, determined when humans could leave Africa. Important facts reveal that the successful migration coincided with a major climatic shift between 70,000 and 60,000 years ago, when monsoon patterns strengthened and pushed rainfall deeper into Arabia. This transformed the Arabian Peninsula into a green landscape dotted with lakes, rivers, and patches of grassland, creating a temporary bridge from Africa into Eurasia. Stone tools found at Jebel Faya in the UAE, dated to around 125,000 years ago, show similarities to African Middle Stone Age assemblages, supporting the idea of early crossings. Yet the groups who left then did not thrive long-term. It took the later climatic alignment to create a stable migration corridor. Another real clue. Genetic evidence shows that the ancestors of all non-African populations derive from a small subset of African humans who lived roughly 70,000 years ago. This means that even if earlier migrations occurred, they either left no genetic legacy or contributed only tiny fragments. All living people outside Africa trace back to the later migration wave, proof of how difficult and rare successful exits were. The out-of-Africa threshold was not a door always open, but a door that opened briefly and then shut again. Inside Africa, Homo sapiens had already developed the skills necessary for long-distance movement, advanced toolkits, fire mastery, flexible diets, and complex social networks. These abilities were forged over hundreds of thousands of years under Africa's unpredictable climate. Once a corridor finally opened, they allowed humans to traverse deserts, coasts, and grasslands far more effectively than earlier hominins. But the final ingredient, the key that turned opportunity into diaspora, was cooperation. Only highly cohesive groups, capable of sharing resources and planning ahead, could survive the journey into unknown and shifting terrain. The missing evidence adds texture to this story. Many early migration routes are now underwater, submerged by rising sea levels after the last ice age. Coastlines that humans once followed, rich with shellfish, fresh water, and game, lie hidden beneath the Red Sea and the Gulf of Aden. Archaeologists suspect that some of the earliest migrants left Africa by hugging these lost shorelines, moving slowly along coastal routes and foraging as they went. Their campsites and tools may be preserved beneath sediments, invisible to us for now. Another important real fact: Homo sapiens did not leave Africa as a single unified group. Instead, the migrants carried only a fraction of Africa's genetic diversity. The groups that remained behind, particularly in Central, Eastern, and Southern Africa, continued evolving in place, maintaining rich genetic lineages that remain visible today. This explains why African populations contain greater genetic variation than all non-African populations combined. Migration filtered diversity. Africa retained its depth. To understand the emotional tone of this threshold, imagine a small group of Homo sapiens around 65,000 years ago, standing at the edge of the Red Sea at a shallow crossing point. The wind is hot, the tide is low. They carry fire embers wrapped in bark, stone blades hafted to wooden shafts, and woven bags filled with dried meat. They know the land behind them intimately, every stream, every cave, every predator. The land ahead is an expanse of shimmering heat. They do not know what lies beyond, but the rains of recent generations have softened the desert. Small patches of green dot the landscape. Game trails lead northeast. Birds migrate overhead. Perhaps they cross in a single night, walking through shallow water or using crude rafts of bundled reeds. Perhaps they wait for many days, watching tides, scanning the horizon, speaking in soft clicks and tones that carry across the wind. When they finally move, they do so not with arrogance, but with cautious hope. They carry with them the memory of African landscapes, the skills forged by African challenges, and the languages born in African throats. They step forward not knowing they will become the ancestors of every person who will one day walk in Asia, Europe, Australia, and eventually the Americas. And yet, Africa does not relinquish them completely. The people who remained continued evolving, diversifying, innovating. Some lineages interbred with those who left upon their sporadic returns. Others stayed isolated in rainforests or along coasts, preserving ancient genetic threads. The out-of-Africa threshold marks the beginning of global humanity, but not the end of African evolution. The continent remained the center of human origins. As this moment settles, the narrative prepares for the next major turn. Once humans left Africa, they encountered other hominin species living across Eurasia: Neanderthals, Denisovans, and others. But every one of those lineages would eventually vanish, leaving Homo sapiens, the African lineage, as the last surviving human species on Earth. When the first waves of Homo sapiens stepped beyond Africa into the wider world, They did not enter an empty landscape. Eurasia was already home to multiple hominin species, Neanderthals in Europe and Western Asia, Denisovans in the East, and possibly remnants of even older lineages in pockets scattered across the continent. These species were strong, resilient, and well adapted to their environments. For hundreds of thousands of years before our arrival, they had thrived in climates humans had never seen: icy tundras, cold steppes, mountainous forests, and deep limestone valleys. Yet, within a brief evolutionary instant, something remarkable unfolded. Every non-African hominin species vanished. Only Homo sapiens, the lineage shaped exclusively in Africa, remained. This section explores the extinction of our rivals, not as a tale of conquest, but as an evolutionary story driven by climate, competition, culture, and the complex interplay of traits forged on African soil. Mainstream paleoanthropology confirms that Homo neanderthalensis, a robust species with average brain sizes slightly larger than ours, lived from 400,000 to about 40,000 years ago. Neanderthals hunted large game, used stone tools, cared for their injured, and produced symbolic artifacts late in their history. In eastern Eurasia, another group thrived, the Denisovans, known primarily through genetic evidence and a handful of bones and teeth dated between 200 and 50,000 years ago. Other archaic humans, such as Homo erectus, lingered in parts of Asia until perhaps 117,000 years ago, while species like Homo floresiensis and Homo luzonensis survived on island refuges. And yet, after Homo sapiens expanded out of Africa, every one of these species disappeared. Real facts show that extinction did not happen instantly. Instead, it unfolded gradually, region by region, over tens of thousands of years. Neanderthals persisted in pockets of Europe long after Homo sapiens arrived in the Middle East. Denisovan genetic signatures suggest that at least some populations expanded and interbred with humans before contracting. The fossil record hints that certain archaic groups retreated into smaller and smaller ranges before vanishing entirely. This pattern implies a prolonged, complex interaction rather than sudden displacement. Genetics provides one of the most important facts in this story. When humans left Africa, they interbred with Neanderthals and Denisovans. All non-African populations today carry roughly 1 to 2% Neanderthal DNA, and some populations in Oceania carry up to 5% Denisovan DNA. This proves that our encounters with other species were not purely competitive. They involved cooperation, shared shelter, mating, and cultural exchange. Yet despite interbreeding, the archaic species ultimately disappeared, suggesting that the African lineage possessed long-term advantages that archaic groups could not match. What were those advantages? Real evidence points toward 4 major factors forged during millions of years of evolution in Africa. 1. Greater social complexity. African populations developed large, interconnected social networks capable of sharing ideas across long distances. Archaeological sites across Africa show patterns of trade, pigments, shells, stone types, moving hundreds of kilometers. Such networks allowed Homo sapiens to innovate faster and retain knowledge more effectively than isolated Neanderthal groups. When climates shifted, Africans had broader cooperative safety nets, while Neanderthals often faced fragmentation. 2. Flexible technology and rapid innovation. Important facts reveal that Middle Stone Age technologies in Africa, beginning around 300,000 years ago, were more varied and sophisticated than most Neanderthal toolkits of the same age. Homo sapiens used bone tools, composite weapons, microliths, and fire-hardened points long before these techniques appear in Eurasian contexts. This flexibility allowed humans to adapt quickly to unfamiliar environments after leaving Africa. 3. Broader diets. Neanderthals were specialized hunters of large Ice Age mammals. When climates warmed or megafauna disappeared, their narrow niche became a vulnerability. Homo sapiens, shaped by Africa's ecological instability, had far broader diets: shellfish, roots, tubers, berries, fish, small game, large animals, allowing them to thrive through rapid environmental changes. 4. Symbolic thought and cultural transmission. African sites like Blombos, Border Cave, and Pinnacle Point show evidence of symbolism, pigments, jewelry, and long-term planning long before these appear consistently in Neanderthal contexts. Symbolic thinking created stronger group identity, allowed abstract communication, and likely improved coordination during hunting and tool-making. These cognitive differences were subtle but cumulative. It is crucial, however, to unravel a misconception. Homo sapiens did not spread across Eurasia as conquerors systematically wiping out their cousins. The real picture is slower, softer, and more shaped by climate than conflict. Around 45,000 years ago, dramatic climate oscillations, rapid freezing and warming events swept across Europe and Western Asia. Neanderthal ecosystems collapsed again and again. Forests turned to tundra. Tundra flipped back into forest. Large prey populations declined. Small, isolated Neanderthal groups faced repeated bottlenecks. At the same time, Homo sapiens arrived with stronger cooperative networks and more adaptable strategies. Contact zones show mixtures of technologies, suggesting periods of coexistence and cultural exchange. Some groups likely lived side by side for centuries. But eventually, as climates pressed harder, Neanderthal numbers dropped below sustainable levels. Isolated populations lost genetic diversity. Inbreeding became severe. We know from fossils like the Altai Neanderthal that some populations were as inbred as half-siblings. Denisovans, too, likely fragmented into scattered refugees as humans spread across Asia. Their genetic heritage survived not through their own persistence, but through interbreeding that folded fragments of their lineage into Homo sapiens. The most important real fact: no archaic human species survived past 40,000 years ago, except our own. The African lineage, Homo sapiens, became the last human species on Earth. This was not because we were stronger or more aggressive, but because Africa had produced a lineage uniquely capable of flexibility, cooperation, adaptation, and cultural resilience. That resilience has emotional weight. To feel it, imagine a valley in Western Europe around 42,000 years ago. Winter presses hard. A small band of Neanderthals gathers in a rock shelter. They light a fire, wearing thick furs, hunting tools arranged near the entrance. Nearby, a small group of Homo sapiens camps along the same river. Their tools are lighter, more varied. Their ornaments, shell beads, ochre markings, glint in the firelight. Perhaps they see each other's smoke in the distance. Perhaps they avoid contact. Perhaps they exchange words. Perhaps they share a hunt. But over generations, the Neanderthal group grows smaller. A failed hunt, a harsh winter, a disease they cannot overcome. Eventually, the smoke from their shelter fades. No one returns to that cave. But the African lineage endures, carrying inside it fragments of these lost cousins, living echoes of species who shaped our journey before disappearing. And as this section softens into silence, the narrative turns toward synthesis. The scattered clues, climate, fossils, genetics, predators, tools, are about to converge. The missing evidence is ready to reveal why Africa alone produced such a species. For more than a century, researchers have collected fragments, fossils buried in ancient sediments, stone tools scattered along eroded lake beds, genetic signatures hiding within our cells, and clues etched into Africa's shifting climates. Each fragment felt like a whisper, a piece of a puzzle too large to grasp at once. But now, as we glide into this final phase of revelation, the scattered pieces begin to align, forming a single coherent truth about why human evolution could only have begun in Africa. The missing evidence, long obscured by time, erosion, and fragmented records, becomes visible through convergence. Climate instability, geological dynamism, predator pressure, tool innovation, genetic bottlenecks, and social complexity all overlap in a pattern unique to one continent. This section gathers those threads, weaving them into a steady, flowing narrative that illuminates Africa not just as our birthplace, but as the only environment capable of producing the species we became. Mainstream anthropology has often presented human origins as a linear progression. Australopithecus leads to early Homo leads to Homo erectus to sapiens, and so on. But real evidence from Africa paints a far richer, more tangled story. The continent was not home to a single lineage, but to many. a braided river of hominin species overlapping in time and space, adapting to microenvironments shaped by the Rift Valley, volcanic landscapes, forests, highlands, coasts, and deserts. These lineages diverged and reconnected over hundreds of thousands of years, sometimes interbreeding, sometimes disappearing without a trace. The missing evidence, unfound fossils, unexplored regions, ghost populations detectable only in DNA, feeds into this mosaic. Africa's geological fragmentation created dozens of isolated evolutionary laboratories, each shaping hominins differently. No other continent hosted such diversity or such sustained evolutionary experimentation. Real facts show that Africa experienced more dramatic climatic oscillations than any other region during the critical periods of human evolution. From 3 million years ago to 200,000 years ago, rainfall belts shifted north and south by hundreds of kilometers in response to orbital cycles. Forests turned to grasslands, grasslands reverted to forests, lakes filled and then vanished, predator guilds expanded and contracted. These environmental pulses repeatedly forced hominin populations to adapt or perish. As we saw earlier, this instability rewarded flexible behavior, diverse diets, innovative tools, and cooperative social structures. Eurasia's more stable environments did not exert comparable pressure, which is partly why hominins outside Africa, such as Homo erectus populations in Asia, remained relatively unchanged for nearly 1 million years. Another important fact: Africa's predator density during key evolutionary periods was unmatched. Being prey for millions of years shaped our vigilance, our cooperation, and our need to communicate, living under the shadow of saber-toothed cats, giant hyenas, and crocodiles, forged an emotional and cognitive architecture rooted in group cohesion and shared awareness. Predator pressure did not sculpt Neanderthals or Denisovans in the same way. Their environments, though harsh, did not impose the same constant danger from apex predators. Africa's unique predator-prey dynamics played a central role in the evolution of intelligence, empathy, and social bonding. The evidence from technology fits neatly into this pattern. The earliest tools, Oldowan flakes, and the even older Lemequian tools, appear exclusively in Africa. The Acheulean hand axe tradition endured for more than 1 million years on African soil before spreading elsewhere. Middle Stone Age innovations, microliths, blades, composite tools, bone points, and symbolic pigments all originated in Africa long before humans left the continent. These technological traditions emerged in response to ecological challenges and opportunities available only in African environments. They were not imported from elsewhere, nor did they arise independently outside Africa until much later. The technological arc of humanity began in Africa and remained centered there through each evolutionary leap. Genetics, perhaps more than any other field, reveals the deepest underlying truth. All humans living today descend from African populations that went through repeated bottlenecks, expansions, isolations, and reunifications. Mitochondrial DNA, Y chromosomes, and autosomal analyses converge on the same finding. Homo sapiens originated in Africa between 200,000 and 300,000 years ago, and all non-Africans descend from a subset of that African diversity that left the continent around 60,000 to 70,000 years ago. The genetic bottlenecks, driven by climate, population fragmentation, and ecological pressures, filtered our species into a narrower lineage capable of surviving unpredictable environments. These bottlenecks occurred inside Africa, not outside. The rest of the world inherited this filtered lineage long after the evolutionary shaping was already complete. The missing evidence, when considered as a whole, tells an even richer story. Fossils like Australopithecus sediba, Homo naledi, and the diverse early Homo assemblages suggest evolutionary experiments we have barely begun to understand. Genetic traces of ghost lineages imply the existence of ancient hominin populations that lived and died entirely within Africa, contributing fragments of their genomes to later humans. These hidden ancestors remain unknown not because they were absent, but because Africa's landscapes, forests, deserts, shifting river basins are difficult environments for fossil preservation. Their absence in our collections is not evidence of their non-existence. It is a silence waiting to be filled by future discoveries. Important facts highlight another convergence. The emergence of symbolic behavior, a hallmark of modern cognition, began in Africa tens of thousands of years before similar behaviors appear anywhere else. Engraved ochre, shell beads, cross-hatched patterns, burial sites, and pigment tools all date back to the African Middle Stone Age. Symbolism did not arise spontaneously across the world. It emerged gradually in Africa as a response to social complexity, communication needs, and cultural evolution. Africa also served as the genetic and cultural crossroads of early humanity. Populations moved within the continent for hundreds of thousands of years, trading ideas, mixing lineages, and spreading innovations. The out-of-Africa migration was merely the final outward ripple of a much older pattern of internal migration. These internal flows ensured that traits shaped in one region, like coastal foraging strategies, pigment use, or new blade technologies, eventually spread across broader populations. To understand this convergence emotionally, imagine standing at a site like Olorgesailie or Blombos, listening to the whispers of time in the wind. The ash layers, stone tools, pigments, and bones each carry tiny echoes of this long evolutionary symphony. You might imagine early humans napping stone beneath a cloud of volcanic dust, others gathering pigment to mark their bodies or tools, others drying meat on sun-warmed rocks. Each community lived in a world shaped by Africa's relentless dynamism. Their innovations were not random. They were responses to a continent that refused to stay still. When the climatic rhythms finally aligned and humans stepped outward, they carried with them all of this. Every adaptation, every neurological refinement, every whisper of culture forged during Africa's long evolutionary crucible. They did not become human after leaving Africa. They left as humans, fully formed in body and mind. This is why the missing evidence matters, not because it changes the outcome, but because it reveals how profoundly Africa shaped every detail of our species. All threads now converge into the final question, a question that this entire narrative has been leading toward. Why Africa alone? Why not Eurasia or Asia or the Americas? As we flow into the final section, the answer becomes clear. Why Africa alone? Why, across all the vast continents and shifting epochs of Earth's history, did only one place generate the lineage that would become human? As we drift into the gentle close of this long narrative, the answer no longer feels like a riddle. It unfolds naturally from the threads we've been weaving, threads of climate, geology, predators, tools, social evolution, and genetic history, all converging into a single, steady truth. Africa was not just humanity's birthplace by chance, but by necessity. No other continent offered the precise combination of forces required to shape a species as adaptable, cooperative, intelligent, and resilient as Homo sapiens. Africa was the crucible, the testing ground, the restless teacher that forged us through millions of years of challenge and renewal. The mainstream facts give us the outline. The all-known early hominin species arose in Africa. The earliest stone tools were made there. Our genus, Homo, originated there, and anatomically modern humans evolved there between 200,000 and 300,000 years ago. But these facts alone do not explain the why. The real answer emerges only when we look deeper at the forces shaping these events. Africa possessed a unique climate engine, one that shifted rain belts dramatically, alternated between wet and dry periods, expanded and contracted forests and grasslands, and changed freshwater systems constantly. These cycles were driven by Earth's orbital rhythms, but Africa responded with extraordinary intensity. Hominins living there faced unstable environments that changed fast enough to demand innovation, but slow enough to allow adaptation. This perfect tempo of instability rewarded flexibility, intelligence, and social cohesion. Other continents did not experience this combination. Eurasia's climates, though harsh, were far more predictable and seasonal. Asia's vast plains offered stability over long periods. North America and South America were not even accessible to hominins until much later. Only Africa presented environments so varied and so changeable that populations repeatedly faced survival bottlenecks that sharpened their cognitive and social abilities. Real geological facts reveal another layer. The Great Rift Valley, Africa's massive fault system, created isolated basins, shifting lakes, volcanic soils, and diverse ecosystems within extremely short distances. Populations separated by lakes or ridges evolved differently, only to reconnect when conditions changed. This pattern created a braided evolutionary network impossible elsewhere. Eurasia lacked such intense geological fragmentation during early human evolution. Africa's landscapes compelled diversification and then blending, weaving multiple traits into the emerging Homo sapiens lineage. Predator pressure is another essential factor. Africa's predator guild during critical evolutionary periods was unmatched in ferocity and diversity. Hominins were prey for millions of years. Surviving required heightened awareness, cooperative defense, and sophisticated communication. These pressures shaped neural wiring, emotional bonds, and group structures that later became foundational to human society. In Eurasia, predator diversity was lower, and many apex predators disappeared earlier. Africa's danger shaped human cognition in a way no other continent could. Tool-making innovation also arose first and evolved longest in Africa. For nearly 2 million years, African hominins experimented with stone, bone, fire, pigments, adhesives, and early symbolic forms. These technological traditions did not arise repeatedly across continents. They emerged in Africa and matured there long before anyone carried them outward. These innovations were responses to local challenges, new prey, shifting water sources, harsh droughts, volcanic landscapes. Eurasian hominins like Neanderthals were highly skilled but developed technologies that were often narrower and more specialized. Africa's diversity demanded versatility. Important genetic facts also play into the answer. Africa's immense size and ecological variety allowed deep population structuring. Different human groups diverged for tens of thousands of years, evolved separately, and then reconnected, blending traits into a shared gene pool. This created extraordinary genetic diversity, the raw material of evolution. Outside Africa, populations experienced far less diversity and narrower gene pools. Every time climate sealed off one region within Africa, evolution took a new turn. Every time climate reopened a corridor, these variations mixed. Nowhere else on Earth offered such long-term cycles of division and reunion. Another real dimension is time. Africa was the only continent where hominins lived continuously for over 6 million years. Eurasian hominin populations appeared and disappeared, often wiped out by climate shifts or replaced by new migrants. Africa, by contrast, remained the central stage of hominin evolution for millions of uninterrupted years. Evolution requires not only pressure but continuity, and Africa's vast refugia allowed hominins to survive every global climatic crisis. The missing evidence, the fossils yet unearthed, the ghost lineages in our DNA, the cultural traditions lost to time, strengthens rather than weakens Africa's centrality. Every new discovery pulls the story back to Africa, reinforcing the continent as the epicenter of evolutionary creativity. Even species we have not yet found, those hinted at by genetic signatures, lived and died in Africa before contributing to the mosaic that became us. The absence of their fossils is not a gap in the story. It is a reminder of how much Africa still hides. To feel why Africa alone, imagine walking slowly across the continent as it existed 500,000 years ago. You move through dense equatorial forest, alive with insects and shadowed by giant trees. Then, the land opens suddenly into a sprawling savanna where herds of antelope graze under the watch of lions. Farther south, the air cools near highland plateaus. Lakes shimmer to the west, stretching to the horizon, their edges lined with the bones of ancient fish and crocodiles. All around you, the earth is shifting, forests expanding, grasslands contracting, storms rolling, rivers moving. Human groups live in pockets, some carving stone tools near coastal caves, some migrating along river valleys, others sheltering in highlands. They are shaped differently by their surroundings, yet all share the same ancestral rhythms. This one continent contains more environmental variety than the rest of the world combined. It is a place where evolution never rests. And through millions of years, Africa shaped something new, something the world had never seen. A creature who could track the seasons, remember water holes, hunt cooperatively, craft tools, tame fire, share stories, comfort children, bury the dead, build symbols, and eventually look up at the stars and wonder. This combination did not evolve anywhere else, because no other continent could produce the pressures, opportunities, and instabilities required. By the time Homo sapiens stepped beyond Africa around 60,000 years ago, we were already fully shaped, body, mind, and culture. Everywhere we went afterward, we succeeded because we carried the lessons Africa taught us. We were the children of its storms, its predators, its forests, its deserts, its firelight, and its endless cycles of renewal. Earth did not produce a second continent capable of forging a species like us. Africa was singular. And as our story softens now toward sleep, let the final imagery fade gently. The warm wind over an ancient savanna carrying the smell of rain. The flicker of a fire reflecting in early human eyes. The quiet hum of insects in the long grass. And the knowledge that every person alive today, every voice, every heartbeat, every dream, was shaped by a journey that began in a single continent under the vast, unending African sky.